Hello student, I am Sanjay Manghnani, Assistant Professor, Mechanical Engineering Department of Arya College of Engineering and IT. This is the part second of the first numerical that we have taken in the last video lecture. In last lecture, we have completed the step number 1 to step number 5. We have completed this step number 1 to step number 5 in the last lecture. Now we will complete our design. This was the problem. We will see what we have calculated in the last lecture. In step 1 we have found that length of the bearing is 240 mm. In step 2 we have calculated the pressure 1.11 Newton per mm square. Then we check the pressure from the table 15.11. The pressure is safe. In step number 3 we assume that C by R is equal to 0.0013 from the table 15.11. This is the table 15.11. In step number 4 we have calculated the value of absolute viscosity Z, and the value of Z we have calculated the value of Z is 0.018 Newton second per meter square. In step 5 we have found the value of bearing characteristic number Zn by P. The value is 14.59 and the bearing modulus from the table is 9.67, and we have found in the last lecture that bearing characteristic number 14.59 is greater than the bearing modulus 9.67. So the bearing will operate under hydrodynamic condition. Now step number 6. So in step number 6 the coefficient of friction F, we have to find the coefficient of friction from table 15.12. Sorry, equation number 15.12. So this is the equation 15.12. Coefficient of friction is Ka Zn by P R by C multiplied by 10 raised to minus 10 plus delta F. Ka, this is the value of Ka, where beta is the contact angle, and for full journal bearing the value of Ka is 0.195 multiplied by 10 raised to 6. Small n is the RPS, revolution per second. So these are the values. We put these values in the equation. Ka, this is the value of Z, n is RPS. Given value is 900 rpm, so we have to divide this value by 60. Pressure 1.11 R by C. In step number 3 we have assumed that C by R is 0.0013, so we have to put this value in this equation. So this is R by C, so 1 upon 0.0013, and delta F, we can take the delta F 0.002, or we can take the value of delta F from the figure 15.1. So generally we take this value 0.002. So the coefficient of friction from this equation is 0.00565. So this is the step number 6. Now in step number 7, 8 and 9, this is the heat consideration of the bearing. In step number 7, first we calculate the heat generated by the equation 15.36, then heat dissipated by the equation 15.40, and then we will check that heat dissipated becomes at least equal to the heat generated. So In step number 7, heat generated can be calculated from the equation 15.36 of the data handbook. The equation is FWV. F is coefficient of friction, W load, and V is the rubbing velocity. This is the formula for the rubbing velocity, pi dn by 1000. So velocity is 7.07 meter per second from this equation. Put all these values in Hg, heat generated. We get that heat generated is 1598 watt. Now step 8 is heat dissipated. Heat dissipated can be calculated from the equation 15.40 of data handbook. We have already discussed this heat generated and heat dissipated concept in the previous video lecture. So the equation HD is equal to C double dash LD. C double dash LD, we have the value of L and D, but for C double dash use table 15.10. This is the table 15.10. These are the values of C double dash for well ventilated bearing, and this is the value for unventilated bearing. So for calculating the C double dash, first calculate the TB minus TA. TB is the bearing temperature and TA is the ambient temperature, 15 degrees centigrade. So this is the value of TB minus TA. We know that TB minus TA is TO minus TA by 2, and TO is the operating temperature, 55 degrees centigrade. TA is the 15 or 15.1 degrees centigrade. We can take 15.1. So this value comes 19.75. So we can take C double dash from this table for 20 degrees centigrade. So this value is 5.670. Put this value in the equation. So HD comes 5.67 10 raised to minus 3 C double dash. This is the diameter of the bearing D, and this is the length. So it comes 204 watt. So heat dissipation is 204 watt and heat generated is 1598 watt. Since the heat dissipated is less than the heat generated, the bearing should be redesigned by increasing the oil temperature, oil operating temperature TO, or we can cool the bearing artificially by water or oil. So let we take the second solution, cooling the bearing artificially. So this is the amount of cooling required, Hg minus HD. HT is 1598 and HD heat dissipated is 204. So the cooling required is 1394 watt. For this, the oil can take this heat, and the equation is ST is m dot S delta T, where m is the mass of the oil, mass flow rate of the oil, and S is the specific heat of the oil. We can take this value from generally 1800 to 2100 joule per kg per degree centigrade, and delta T is the temperature difference between the inlet and outlet temperature. Generally we can take this value 10 degrees centigrade. So 1394, that is cooling required 1394 watt. So 1394 is equal to m dot 1900, this value S, we take 1900, and delta T 10 degrees centigrade. So it comes m dot is 0.073 kilogram per second. M dot is mass flow rate for the cooling, mass flow rate of the oil for the cooling required. So this is all about the bearing, general bearing design. Now in next video lecture we will take some another example of journal bearing. Thank you.